Okay, good morning, everybody. I'm gonna explain because I haven't request for explaining this topic, and I know they already made a video about this, but there were a few errors that I want to correct. So, anyways, the topic for today is uh, let me use the pen. Quasi-isentropic compression implemented on lamps. Okay, so just give me a moment so I can uh, turn off the camera. Okay, so just let me go here and enlarge the presentation. So, anyways, what we plan to learn today is the following. Number one. So we're gonna learn what's quasi-isentropic compression, okay? And then we're gonna provide an example of how to run a LAMMPS script to run a molecular dynamic simulation for a uniaxial quasi-isentropic compression, okay? Then I'm gonna go into two scenarios. The first one is when the strain rate is gonna be variable, and the second one is when you have the strain rate is going to be constant. And then finally we're going to learn how to do the verification of the results. So in case that you want more information, here's a link that probably you can look at this presentation. Okay, probably this is for the people who have the PDF, and because if you already see in this video, you already have access to the to YouTube. Anyways, continuing with the presentation, a few vocabulary that's good to learn before you start with the main topic is what is LAMMPS? When LAMMPS is a large-scale atomic molecular massive parallel simulator. It's a molecular dynamics program from Sandia National Laboratories. Then the second one, well, what is molecular dynamics? Molecular dynamics is a computer simulation method for analyzing the physical movements of atoms and molecules. Then we're going to Quasi. It's a thermodynamic process that happens slowly enough for a system to remain in internal thermodynamic equilibrium. And then isentropic is an idealized thermodynamic process that is both adiabatic and reversible. And finally, in statistical mechanics, the microcanonical ensemble is a statistical ensemble that represents the possible states of a mechanical system whose total energy is exactly specified. So, one person asked me this question. Another reason why I decided to do this video, because well, I have right now free time, so this is for me like a hobby. But anyways, it says read the following: Dear Oscar, I had read a new LAMMPS manual file, but cannot find any comment about quasi-isentropic compression impacting. So I read your guide document of modeling quasi-isentropic compression via LAMMPS. It is very wonderful. I have been encouraged for testing a modified C code of LAMMPS for quasi-isentropic simulation. However, I had two questions. Question number one, after the make of the new C code, is the quasi-isentropic method in LAMMPS can be used for various materials, such as molecular crystal. Could you please give me more details about tutorials via my email for Modify and Hack Guy? Thanks for your reading. So the purpose of this lesson or presentation is to answer these two questions. I can see right now that the answer to the first question is yes. Okay, you can use this for any kind of materials, not necessarily. I mean, because it only depends on the strain rate. And for the second answer, that's what we're trying to review in the next slides. So just to give a background history, so I think that in 2013 I made this beginner guide for modeling quasi isentropic compression, and here and in this one, uh, I remember that I used a hack. What happened is, and actually you can see right here on the, because it's in ResearchGate. But anyways, on that time, there was no way to quasi-isentropic compress the materials, right? And I think that they read this guy, they decided to do something about it. So on that time, you had to do like a hack, because if you go into LAMMPS, you have different profiles, right? Like the T rate or engineer strain. I mean, all these are the same. It does not, I mean, all these are running by the same principle. For what I did at that time, I went into the one of these profiles on LAMPS, and I entered my strain rate form, and that way I was able to compress quite isentropically. But anyways, right now at this time is not, you're not on the need to run any hack, because LAMPS already have the option to do quite isentropic compression without having to go and modify the program. So just going into more information about what's quasi-isentropic process, okay? So quasi-isentropic compression refers to the process of compressing without a change in entropy. Quasi-isentropic compression is ideal for high-strain deformations because there's not enough time for heat transfer. And then here I'm explaining that from the first law of thermodynamics, we can state that the heat flux is zero when the total energy rate is equal to the mechanical work rate. In other words, and here we have this definition right here. Okay. Now, I decided to explain this a little bit further. I mean, if you remember the rule of thermodynamics, the energy or internal energy is equal to the Q, that is the heat, plus the work. Okay. Also, you can have here a plus, or you can have like a minus. It doesn't matter. Okay. So if I want to find the flow rate, okay, now it's finding the energy rate respect of the time. Okay, and probably you had to know a little about calculus, but that has to be equal. If you remember, Q is equal to the temperature multiplied by the entropy S plus the work I'm gonna define as pressure times the volume. Okay. Now, if we apply the chain rule to this, like I did here for the energy rate, so that means that the energy rate is equal to the change in temperature times the entropy plus the temperature, and here we have the entropy, the rate of the entropy, plus the pressure, the rate on plus volume, plus P volume here. Okay, so if we, and actually that way, if we draw the temperature, and here we have the temperature over time, if the temperature increase as a line, as a straight line, yes, and probably you remember that this is like if the temperature has the behavior of a straight line like mx plus v, okay, that means that when we find the rate of temperature, that's gonna be zero, right? So the temperature has to behave linearly. If that happens, then this part of the equation removes, it's gonna become zero, right? And also, if the pressure is also behaving linearly, we can remove this part over here, okay? So that means that the energy rate is equal to the temperature times the change in entropy plus the pressure times the change in volume, okay? Now, if the energy rate, okay, equals to the pressure times the change in the volume, that implies immediately that the change in the entropy has to be equal to zero. Okay, So that means that there was no change in entropy on the process, okay? But for that to be true, the change in the temperature has to be zero, so it means the temperature has to increase as a straight line, and also the pressure has to increase like in a straight line, okay? And this is actually what we are trying to define right here in this equation, okay? So in this case, because we are compressing uniaxially, it means that the energy rate has to be equal to the, in this case, if we are compressing uniaxially on the x direction, it has to be the pressure tensor in x times the volume rate. Okay, so if we have this, that means that we have something that is defined as quasi-isentropic. Okay, so going into how the deformation of a body, okay, the deformation of a body, and actually that was from my tutorial guide, is given by this formula right here. The length as function of time equals to the initial length multiplied 1 plus the strain. Okay, the strain is a percentage function. It can also be negative here. Okay, so we have like we can do like a compression, or we can do like a stretching. So if we define, for example, a strain of 20%, okay, and 20 is equal to because we had to have this in decimal 0.2, okay, because the strain goes from 0 to 1, and then this strain right here we plug it into the equation, okay. So that means that the final length of the computational box is gonna be equal to the initial length, okay, and here we can put like a negative because we're compressing, so it's gonna be 1 minus 0.2 is 0.8. Okay, so that means that the final length is going to be equal to 80% of the initial length of the computational box. Okay, now I can use any strain or any epsilon right here. Okay, and the epsilon that we're using is specifying right here. So having this epsilon, we can compress the box quasi-isentropically, but you don't have necessarily to use this epsilon. Okay, so in this case, look, that the epsilon is changing as function of the time, and then when we have the epsilon, I can find the strain rate of the computational box, and I need the strain and the strain rate. And if I have that and I plug in into my equation right here, then I can do any kind of deformation into the body. Okay, so I'm gonna do an example right here. When I had a simulation of BCC tantalum using around 4,000 atoms, okay, we're using a EM interatomic potential, and we are at 300 Kelvin. And we're gonna try to do a total compression of 20%. The strain rate max is gonna be 3.3 times 10 to the power 9 seconds to the negative 1. Time step is gonna be 1 femtosecond. And then we can find the compression time, tau, by saying that tau is equal to 6 epsilon divided by the Emax, the maximum strain rate, okay? Here we're assuming, yes, if we plot the strain rate right here, we're assuming that the strain rate is gonna start at 0, gonna increase, and then the strain rate is gonna decrease, right? And here we have this right here in the middle is gonna be the Emax. Okay, and this is running from 0 to tau, right? So the only condition to compress something quasi-isentropically, it only depends on does the initial, okay, does the epsilon at 0, and does the epsilon at the final time that we define as tau, that has to be the same. Okay, so in this case, it's gonna be equal to 0. If that happens, we can deform quasi-isentropically. So it means that we don't have to use this strain or this epsilon. We can use any strain. Okay, we can use, for example, something that's like sine square. Okay, that's also as a strain rate. That's also an option to compress something isentropically. Okay. Or if you want, you can use like a constant strain rate. So you can, for example, and that's for the example number 2, you can have like an epsilon here, and the epsilon can be in a straight line. And that also can be compressed isentropically. So anyways, here I'm showing the profiles of the, if we run a simulation, actually I'm gonna go here into the script. Okay, so here we have how to compress isentropically. So we initialize the simulation. Remember that the units that we're using were metal, okay? So we're using the units metal. It means that the time has to be in picoseconds. The temperature has to be in Kelvin. So we define the variables right here. The initial temperature, the percentage of compression, the timestamp that here is 0.001 picosecond, that is equal to 1 femtosecond. Okay, so that's what we are using right here, right? But we had to have the correct units. Here we define the run time, okay, and here I had 2 options. So I'm gonna just go here for removing this. Okay. Here I made it for 2. I made it for a constant strain rate and for a variable strain rate. Here we have the time run, okay, and here we're gonna construct our PCC lattice. In this case, gonna be tantalum. We're using the Ravello potential. This is optional, yes. Then the first thing that we do, we're gonna equilibrate the system. So we know that it's running at 300 Kelvin. Once we do the equilibration, we're gonna save the initial length of the computational box. And once we have that, we can start with a deformation, okay? So for the deformation, we had to use a variable displace and a variable rate, okay? On previous versions of LAMMPS, there was no way, okay, to do this. So I needed to hack the program, right? But right now it's not necessarily, and hopefully when they read this, they decide to do something to run compressions using different epsilons, okay? So I'm gonna comment this because here we're gonna go here into my variable displace and variable rate. This right here, yes, this right here that I'm specifying is exactly what I have in my PowerPoint. Here, right, when I define, probably, let me see if I can erase this. Okay. I have in this epsilon right here, and I have in this strain rate. So this is what I'm defining here, and variable displace and variable rate. When we had that, we had to run in a microcanonical, and then we're gonna use fixed form. Okay, we're gonna use the variable, and then my displace and my rate. Okay, once we have that, we have our output, the strain, the pressure, the volume, the temperature, everything that we want to have out. Okay, so I'm gonna run a simulation of this, but I'm not gonna use 4,000 atoms because it will take a lot of time. But here I can put like 5, 5, and 5. So I'm gonna make a small lattice. And then here I can go and run the program. Okay. So here you can see that we're doing the equilibration and then we're doing the compression. This is really fast, right? And actually see here, let's see, we're working on this. Yeah, here we're seeing how we're compressing the computational box. Okay. You really can look at the temperature. Okay. So this has to stop when the compression reaches 20. Okay. So right now it's running. So we had to wait a little bit. Because we are doing a compression, if you remember here, we're doing a compression of 20%. Okay. So right here we can see that it's already at 0.12, 0.13, and it's 0.14. So this has to stop with 0.20, right? So it's running, okay? 0.16, 17, then it's almost going to end at 0.20. There we go. So when we reach 0.20, the program stops, and then we have compressed quasi-isentropical. It only took like here, according to this, 2 minutes. So anyways, once I get my outputs, right, I can see the profiles of the pressure, the temperature, and on the X, etc. I want to say here the following. If we look at the temperature, look, that is a... Oh, I want to use a pen. I'm sorry. Okay, if I go here, look at the temperature. Here is constant, right? Now, here's something that's happening. Okay, that's the reason why we had an increase in the temperature, and here we also had decay on the shear, and here also we see a decay on the pressure, right? But here the temperature is in a straight line, then here the temperature is again in a straight line, and here the temperature is again a straight line. So that means that if we go back, this is gonna be 0, okay? Now also the pressure is gonna be 0, and then having that, okay, then we only have to run to see if the total energy is equal to the pressure on X times the volume rate, right? So here we continue, we can see here that if we look at the PAX, okay, times the volume rate, that's gonna be equal to the energy rate, right? So we see that the red line and the black line are almost all the same, right? So how I do this? Well, I go into my, and actually I'm using Octave, right? So I grab the strain, the volume, the pressure on X, then the total energy, that is from my molecular dynamic simulation, right? Okay, here I have my outputs, okay? So once I do that, I can find the difference in the volume. I can find the rate work by multiplying the pressure on X and the difference in the volume, and then we had to convert that into electrovolts. The reason why I had here 160.21. Then I can find the rate on the energy. Yes, and here I'm finding the difference between the two. Okay, but then I output this into another file so I can visualize, right? So if I do and I take the difference between the two, it's gonna be pretty close to 0. Okay, not exactly 0, but it's close to 0. The reason I think is because we're only running with 4,000 atoms. Okay, so that's not enough. But this is indeed really good, and this is quite isentropic. Okay, now if we go here, we're gonna do another example with a deformation of a body is constant, right? So here the strain rate is it's only a horizontal line, so it means the strain rate is always the same. So it's the same simulation for 100,000, no, I mean 4,000 atoms, 300 Kelvin. The compression is 20%, but here the strain rate is always the same. Yes. So what I did is only to change the space and the rate to this right here. So if I go back to my LAMMPS code, here, yes, I only have to comment for the one cross variable, then I use this tab over here. Then I gonna go here and I'm gonna use the variable rate. We have the strain is constant, right? So now we're using this variable rate right here. Okay, So it all is the same. Okay? All is gonna be the same. So I can run this. Okay. But if you run this, you're gonna see again, right? That if we plot the energy on red and the workflow, okay, look as they are the same. Okay, so now the profile is gonna be different, but it's the same. We see that this is quasi-isentropic, but the same condition that Pxx times the volume rate has to be equal to the flow and the energy, and we see that's true, and we see it right here, right? So that's another way to verify this. So just to end, okay. Things I learned today, things I found interesting, and questions I still have. Okay. So just to make the closure, okay, before when I made this in 2013, okay, and actually you are more than welcome to read this in case that you want more information. When I did this in 2013, you needed to hack the program, but hopefully when they saw this, they decided to define these new variables right here. And I'm gonna increase the screen. So they decided to define a variable displays and a variable rate, and with that, actually, you can compress the computational box in different ways, not only isentropically. So yeah, I mean this, like I was saying right here, if we go to question number 1, can I use this for any material? Yes, because it only depends on the epsilon, right? It only depends on this. Okay, so the answer is this can be done for any kind of material. Here I'm using tantalum, but it can be done for a polycrystal or whatever, right? Because it's only the way that we are deforming the computational box. So anyways, thank you. If you have any comments, please let me know. And have a wonderful day. I really appreciate your time. Thank you.